Good morning, kids. Today we're going to learn about L'Hopital's rule. So you should have this note sheet that says Notes on L'Hopital's rule and hyperbolic functions. Calculus 1, Mrs. Slack-Joles, that's me. And what we're going to do is today, on the 9th, we're going to cover this. And then on the 11th, I'm going to cover the hyperbolic functions. So even though this is one sheet, we're going to use it for 2 days. If you look at the end of the sheet, well, it doesn't say it on your sheet, but this is going to be your homework. I believe that the page 225, 7 through 37 odd, and 61 is the L'Hopital's homework, and that will be the homework that is due next class. And then 234 to 235, 13 to 29 odd, is the hyperbolic homework, and that's going to be the homework that will be due Friday after you have the lecture on Wednesday. Now, here's the thing. I may have these confused because I don't have a book at home, so look at it. If it says it's homework on L'Hopital's rule, then you're in the right place. If it doesn't, then look at page 234. That'll be L'Hopital's homework, but I'm pretty sure it's this first homework that you'll be doing tonight. So, getting on to the lecture, L'Hopital's rule is a very, very powerful tool for calculating limits. And the time that we are allowed to use L'Hopital's rule is when we take a limit and we go ahead and we're trying to take the limit and the top and the bottom of the limit both approach infinity, or the top and the bottom of the limit both approach 0. If either of those things happen, then we can use L'Hopital's rule to calculate the limit. And what it says is, it's crazy. It says that the limit of a quotient, where you have one function in the top, another function in the bottom, okay, the limit of f of x over g of x is always going to be equal to the limit of the derivative of f of x over the derivative of g of x. Now this is you're only allowed to use this when the top and the bottom both approach 0, or when the top and the bottom both approach infinity. Because any other time you're going to figure out what the limit is, right? I mean, if you're either going to get a number, right? The things that can happen with a limit, right? You can have it just approach a number to begin with, right? You can have the limit where you get 0 in the top, right, over something, and that means the answer is going to be equal to 0, right? Or you can get a limit where the top approaches some number and the bottom approaches 0, and that's going to give you a limit of infinity. Okay, so those things can happen. You can also have various things happen. You can have it vacillate. You can have a situation where you have the top approaching infinity and the bottom approaching a number that would approach infinity. You could have the bottom approach infinity, the top approach a number that would approach 0. So all of these things are review for you. But the situation where you have 0 over 0, top and bottom both approach 0, or infinity over infinity, enables you to use L'Hopital's rule. And that's really the only time you will ever need to use it, because otherwise you're going to get an answer. So what we do when we apply L'Hopital's rule is we just take a new limit, and we take the derivative of the top and the derivative of the bottom. Now notice, this is not quotient rule. We're not taking the derivative of a quotient. We are taking separate derivatives of the top and the bottom of the fraction and taking a new limit. All right. First thing we have to do with L'Hopital's rule, though, is show that we're allowed to use it. So if I plug 0 into the top of this, I get 5 times 0, which is 0. If I plug 0 into the bottom of this, I get tan of 0, which is 0. So once I've shown that the top and the bottom both approach 0, I can then use L'Hopital. So I can say this is equal to the limit as x approaches 0 of the derivative of the top is 5. The derivative of tangent is of x, tan of x is secant squared of x. So now, what have I got? Well, I have 5 over secant squared of x. Now let's see if we can go ahead and do that limit. All right. Well, the limit as x approaches 0 of 5 obviously is 5. The limit as x approaches 0 of secant squared of x is secant squared of 0. The cosine of 0 is 1, so when we flip the cosine we get the secant, so that's also going to be 1. And when we square 1, we get 1. So this is going to equal 5 over 1, which is 5. Now, hard to determine that from this back here, but this powerful L'Hopital's rule allows us to do that. Let's look at the next one. If we plug in here, the top, if we plug in 5, what do we get? Well, the top approaches radical 5 minus 1 minus 2. The bottom approaches 5 squared minus 25. So the top and the bottom here, the top, 2 minus 2, approaches 0. Bottom, 25 minus 25 approaches 0. So once you've shown it approaches 0 over 0, by plugging in, now you can use L'Hopital's rule. So we say this is this limit is equal to the lim as x approaches 5 of, well, radical x plus 1, when I take its derivative, that's x plus 1 to the 1/2, right? So that's 1/2 times x minus 1 to the negative 1/2. Times the derivative of the inside, which is just 1, and then the derivative of 2 is 0. So you get 1/2 x minus 1 to the negative 1/2 in the top. Take the derivative of the bottom, you get 2x. Well, the bottom clearly does not approach 0 anymore, so now we know we're not going to do L'Hopital's again. We're going to go ahead and solve this limit. Before I solve the limit, I'm going to clean it up a little. So this 2 and the x minus 1 to the negative 1/2, I'm going to put in the bottom. So I get the x approaches 5, limit x approaches 5 of 1 is the only thing left in the top. The 2 can go in the bottom, so you have 2 times 2x times radical x minus 1. All of that is in the bottom. So now we put that in, we plug in, so that's 1 over 2 times 2 times 5 is 10 times radical 5 minus 1, so radical 4. So that gives us 1 over 2 times 10 times 2, or 1 over 40. Okay, so this L'Hopital's rule is pretty great stuff, I mean, from my perspective. All right, pi, remember kids, pi is a constant, so when you take its derivative, it's going to go to 0 if you end up doing L'Hopital's on this. Okay, so let's go ahead and plug in 3 theta plus pi. So that's 3 times negative pi over 3. This is the limit as x approaches negative pi over 3. So 3 times negative pi over 3 plus pi is equal to 0. So the top is approaching 0. Bottom, sine of negative pi over 3 plus pi over 3, or sine of 0, which also approaches 0. So you have 0 over 0 again, so we're going to use L'Hopital's. So we go ahead and we say that this limit is equal to, and I'm going to come down here for this next part, the lim as theta approaches negative pi over 3 of derivative of 3 theta is 3, derivative of pi is 0. So you get 3 on the top. Derivative of the sine of something is the cosine of that thing, so it's cosine of theta plus pi over 3, and then times the derivative of the inside, which is 1, right? So now you have that. The top clearly cannot approach 0 again, so we're not going to have to use L'Hopital's again. By the way, you can use it over and over again if need be. So we're just going to plug in now. So this is equal to 3 over cosine of negative pi over 3 plus pi over 3. Well, that's cosine of 0, and cosine of 0 is equal to 1. So this is 3 over 1 times 1, which is 3. Done. Let's look at the next one. We have just a few more left here. My chicken is almost done, so It's really important to get through this quickly. I have the lim x approaches negative 3 of x squared plus 2x minus 3, 2x squared plus 3x minus 9, so let's plug them in. So if I put a negative 3 in here, I get negative 3 squared plus 2 times negative 3 minus 3. That approaches 0. In the bottom, I get 2 times negative 3 squared, so that's 2 times 9, which is 18, plus 3 times negative 3, which is minus 9, so that's 18 minus 9 is 9, and then we minus the 9 at the end, so that approaches 0 as well. So we have something approaching 0 over 0, so we go ahead. This is going to be equal to the limit as x approaches negative 3, derivative of the top, 2x plus 2, derivative of the bottom, 4x plus 3. By the way, if we did this by dominant powers, we'd get 1/2, right? So checking this out as we go forward, you're going to notice that L'Hopital's rule is consistent with, oh, wait a minute, we couldn't do this by dominant powers. Oh, strike all of what I just said about dominant powers. It's not approaching infinity. I'm a goofball. Sorry. All right, so we're going to plug the negative 3 in. So we get 2 times negative 3 plus 2. So 2 times negative 3 is negative 6 plus 2. And then in the bottom, 4 times negative 3 is negative 12 plus 3. That's going to be fine. So negative 6 plus 2 is negative 4. Negative 12 plus 3 is, well, let's see here, negative 9. So it's going to be equal to positive 4/9 because 2 negatives divide to give you a positive. So that's that one. Let's look at the next. Lim x approaches 2 of this, so we plug the 2 in. 2 squared minus 5 times 2 plus 6. Okay, so 2 squared is 4 minus 5 times 2. That's 4 minus 10 plus 6. That's the top. The bottom is approaching 2 times 2 squared. 8 minus 2. Let's see here. 2 times 2 squared is 8. Yep, minus 2 minus 7. Well, check it out. See, now in this one, 2 squared is 4, 5 times 2 is 10, and then you got 6. So the top is approaching 0. Hey, but what's the bottom approaching? Negative 1. When you have a 0 on top and a number on the bottom, then the whole thing approaches 0. Okay? Do you have to use L'Hopital's? No. Should you use L'Hopital's? No. As a matter of fact, if you used L'Hopital's on this, you would get the wrong answer. You are only allowed to use L'Hopital's if you start out with something that approaches 0 over 0 or infinity over infinity. So in this problem, you would not use L'Hopital's. It's just as important to know when not to use it as to know when to use it. All right, so let's look at the next one. The lim x approaches 0 of x plus 1 minus e to the x. So this top one, I get 0 plus 1 minus e to the 0. And in the bottom, I get 0 squared. So the top approaches 0, the bottom approaches 0, because the top is 1 minus 1. So I have 0 over 0 here, so I'm going to go ahead and take a derivative. All right, so this is equal to the lim x approaches 0. Derivative of the top, derivative of x is 1. Derivative of e to the x is e to the x. In the bottom, 2x is the derivative of x squared. Well, check it out. You plug a 0 in the top, what do you get? Well, you get 1 minus 1, which gives you 0 in the top again. You plug a 0 in the bottom, check it out. You get 0 again, so it's 0 over 0, which means you're going to use L'Hopital's yet another time. So let's go ahead and do that. I'm going to shrink this up just a tad so I can be a little consistent. I really like consistency. So I'm going to go down below here and say this is equal to the lim x approaches 0 of, well, the 1 is going to go to 0. The negative e to the x is going to be negative e to the x because you're taking its derivative, right? And then the derivative of 2x is 2. So now, what do you get? Well, the top is going to be e to the 0. So it's negative e to the 0 over 2. So that equals negative 1 over 2. Done. Let's look at number 7. Oh, this one looks pretty ugly. Natural log of cosecant of x, and then x minus pi over 2 squared. Alright, so the top, let's see what happens. Well, that approaches the natural log of the cosecant of pi over 2. I know you all know what that is off the top of your head, right? And then the bottom is pi over 2 minus pi over 2 squared. Well, cosecant of pi over 2. Well, cosecant is the reciprocal of sine. Sine of pi over 2 is 1. You flip a 1, you get a 1. So this is the natural log of 1, and we all know that the natural log of 1 is 0. So the top approaches 0. The bottom, pi over 2 minus pi over 2 is 0. Square 0, you get 0. So this does approach 0 over 0. Got to use L'Hopital's. Ooh, this one's a toughie, right? It's not as easy as the rest. So let's go ahead. This is the lim. X approaches pi over 2 of, well, the natural log of cosecant of x. All right, so that's equal to 1 over cosecant, 1 over cosecant of x times negative cosecant x cotan x. That's the derivative of that, right? Because the derivative of the natural log is 1 over whatever's on the inside, and the derivative of the cosecant is negative cosecant x cotan x. Check it out. What happens here in the top is these two will cancel each other. So you'll end up with a negative cotan x in the top. In the bottom, we do 2 times x minus pi over 2, right? Because it's something squared. The derivative of something squared is 2 times that something to the first power times the derivative of the inside, which in this case happens to be 1, so we don't need to write that really. So now what happens? Well, cotan x. Cotan is the reciprocal of the tan function. All right, so what is the tan at pi over 2? Well, tan at pi over 2, if you recall, this is what your tan function looks like. This is pi over 2. So the tan function approaches infinity at pi over 2. But if we take and we take the reciprocal of infinity, 1 over infinity gives us 0. Okay, 1 over the concept of infinity gives us 0. So the top of this is approaching 0. The bottom is 2 times pi over 2 minus pi over 2. That's also approaching 0. So we got to do it again. So let me shrink this up a bit, move it up a bit, and we will do it again. So this is equal to the lim as x approaches pi over 2 of, well, derivative of negative cotan x. Well, derivative of cotan x is negative cosecant squared x. So the derivative of negative cotan x is cosecant squared x. I hear a baby crying. And then the derivative of 2x minus pi, right? Because this, if I distribute, it's 2x minus pi, is just 2. Okay, so now we're going to get to where we need to be, right? So let's see what everything approaches. So the top is going to be, the bottom is going to 2. So we know we're going to get an answer here. So we got cosecant squared of pi over 2. That means take the cosecant of pi over 2 and then square it all over 2. Okay, so the cosecant is the reciprocal of sine. Sine of pi over 2 is 1. We take 1 and we take its reciprocal. It's still 1. We square it. It's still 1. So the top is 1, the bottom is 2, and we're done. And here is the last problem, and then we're going to go to the homework assignment. So we have the lim as x approaches infinity of x squared over natural log of x. Well, x squared approaches infinity as x approaches infinity. Natural log of x approaches infinity as x approaches infinity. Whenever you have infinity over infinity, you're going to go ahead and use L'Hopital's. So let's go ahead and take the derivative of the top and the bottom. So if I take the derivative of the top, I get 2x. If I take the derivative of the bottom, I get 1 over x. Of course, I want to simplify that, so I'm going to just go ahead and multiply top and bottom by x. If I do that, check it out here, x. Hi, Robbie. You want to say hi to everybody? Say hi, everybody.
Hello, buddy.
All right, now you have to go in the other room, okay? You can't touch anything. Please go in the other room with Daddy. Oh, good job, buddy. Love you. Okay, so now what we're going to do is this x, oops, I forgot my little green marker. You guys are probably done already anyways. The x's cancel, so we end up with lim x approaches infinity of 2x squared. Well, the limit of 2x squared as x approaches infinity, of course, is infinity. So that would be the answer to that. So now that's where we're going to stop for today. And again, I showed you the homework at the beginning of class. I just want to draw your attention to it again. Page 225, 7 through 37 odd, and 61. If that's not a bunch of limit problems, well then go to the other assignment here. I think this is the right assignment for L'Hopital's. So page 225, 7 through 37 odd, and 61 should be on L'Hopital's rule. Alright, so kids, have a wonderful day. I'm going to be back with you very soon, so I'm excited about that. Have a great day. Bye.